When we talk about AI, we tend to use these kind of fuzzy human-like words. But what if we had a much sharper, more engineering-focused language to design these incredibly complex systems? Well, today, we're going to explore a really fascinating framework that borrows ideas from physics. Not to say AI is physics, but to create a sort of Rosetta Stone for AI architecture. It's a huge shift from just describing what an AI does to precisely engineering how it does it. So let's dive in.
So take a look at this. On the left, that's pretty much where we are now, the messy present. We use these vague, anthropomorphic terms like hallucination or vibes to explain what's going on. But on the right, you can see a much more structured future. The idea here is to swap out that mess for clear, defined engineering parts, like a bounded observer or directional tension. This isn't just about new labels. It's a completely different way of thinking, moving from describing behavior to actually designing the system's core mechanics.
And this is absolutely crucial to get right. This framework is not saying that AI is literally physics. No way. Think of it more like a design language bridge. The real goal is to get a portable, reusable structure, a blueprint that we can all use to build and debug these systems. The vocabulary from physics just happens to be an incredibly powerful and compact way to talk about that structure.
Okay, so how do we actually start using this new language? Well, the framework gives us a map, a guide called the runtime cycle. This is going to be our narrative backbone, the fundamental loop of operations for any AI system that's designed this way.
And here is that cycle. Pretty simple, right? It's got 6 key stages: see, hold, move, judge, close, and replay. We're going to walk through each and every one of these to build out this powerful new vocabulary piece by piece.
All right, let's kick things off with the first 2 stages, see and hold. This is all about how a system actually perceives its world and then grabs onto that information to make it stable and useful. First up, see. An AI system isn't some all-knowing oracle. It has what's called a bounded observer. Its perspective is fundamentally limited by its compute, its tools, its memory. You get the idea. It sees the world through a projection path, which you can think of like a specific prompt or a certain chain of tools that basically shines a spotlight on one part of the problem it can actually see and work with.
So this leads us to a really critical engineering rule. An AI doesn't see the truth in some absolute sense. It only sees what its current limitations allow it to stabilize and make sense of. If you change that projection path, you change the observer's bound, and you might reveal a completely different structure.
So after seeing something, the system has to hold it. The system's state is just, what it's currently holding in its memory. But the real goal here is to create density. Now, density isn't about having more tokens or a longer chat history. It's about building organized, reusable structures. Think of a validated JSON schema or a tightly compressed bundle of evidence. It's quality over quantity.
Okay, so the system has seen something and is holding a stable structure. Now we get to the really dynamic part of the cycle, move and judge. This is where the system takes action and makes critical decisions.
So what actually makes the system move? The best analogy is a ball rolling down a hill. The force is the initial push, that pressure to reach a goal. The ball rolls across a potential landscape, which is really just the shape of the hill itself, defining the paths of least resistance. And finally, you have fields, which are kind of like the wind or gravity, influencing the entire system and shaping where that ball ends up going.
But this movement isn't just chaos, right? It has to pass through the judge phase. Constraints are the hard boundaries, the rules that absolutely cannot be broken. Then there's adjudication, which is the ultimate filter that decides what is merely possible versus what is actually acceptable. Any path that doesn't make the cut gets filtered out. This process creates something called dissipation. And that's the rework, the wasted compute, the price the system pays for exploring a bad path. Okay, so after the system has moved and been judged, it needs to commit to a final outcome and create a durable record of how it got there. This brings us to the last 2 stages of our cycle, close and replay. So how do we measure progress in a system that's supposed to be reasoning? It's definitely not by counting tokens. The really important concept here is the semantic tick. This is the real unit of progress. It's a complete bounded episode of work that ends in a solid, transferable result, like a fully validated step in a longer plan.
And how does the system remember what happened?
Well, a simple chat history is just a log of what was said, but a trace, now that is something else entirely. It's an irreversible, auditable ledger. It tells the story of how a decision was made, not just what the final answer was. So a chat history might just show you the answer, but a trace would show the 3 different tools the AI tried, the one that failed, and exactly what evidence it used. Now we get to what might be the most powerful, most transformative idea in this whole framework. It's all about how we deal with errors, with uncertainty. This is the big aha moment, where we stop seeing them as bugs or failures and start treating them as structured, valuable pieces of information. Look, strong systems understand that closure is rarely perfect. When an output is produced, there's almost always a residual left over, the bits and pieces that couldn't be fully resolved or flattened out. Instead of just ignoring this or hiding it, a robust system governs it, treating it as a first-class output in its own right.
And this residual isn't just a junk drawer, it's categorized. For example, you might have an ambiguity budget, which is basically the system saying, here's what I'm still not sure about. Or a fragility flag, which marks a result as usable but brittle. Or you could even have conflict mass, which is a structured contradiction. That's not a bug. It's an honest report from the system about the limits of what it could see.
So, when you put all of these pieces together, what's the big picture? What is the fundamental architectural shift that this new way of thinking gives us?
It really boils down to these 3 massive moves. Number 1, we move from messy, endless chat histories to a dense, maintained state. 2, we stop measuring progress with meaningless token counts and start using powerful semantic ticks. And 3, we stop trying to hide errors and start embracing active residual governance. And you can see that whole shift visually right here. We're moving from unstructured logs to dense held states. We're going from just counting words to counting meaningful completed episodes of work. And we're moving from trying to pretend every problem has a perfect answer to explicitly preserving ambiguity, flagging fragility, and managing conflict. Ultimately, the whole point of this is to build systems that preserve their invariance, their core non-negotiable rules and structures, no matter how big or complex the task gets. That is the real path to building AI systems that are genuinely robust, reliable, and trustworthy. Which leaves us with one final, big question to think about. What new kinds of things could we build? What new capabilities could we possibly unlock if our AI systems were designed from day one with this kind of deep structural clarity and really intellectual honesty?